Okay, so hello everyone. I hope everyone uh, is doing okay. First, I'd like to thank the invite to be here to talk here a little bit about my work. As you can see in the title, it's not quite related to astrophysics or cosmology, but well, I'll try to make it interesting. If not, if it's boring, use this time for an nap or whatever. So first, I'll talk a little bit about my background. Why did I study? And then I'll try to explain some concepts that I work with in my research. So my name is Diogo Mendes. I am 23 years old, turning 24 next week. And I'm from this little town, Paredes de Cora, where you're spending your 2 weeks. I hope 2 amazing weeks. And I'm not sure if you already been to the town center, but it might look that nothing happens here. But actually, I had the opportunity during my high school to do a lot of fun stuff here. For instance, I did a music course on guitar. I also took part in a camping and trekking club where I had the opportunity to visit a lot of cool places. I did a nice school Erasmus in Denizli, Turkey. And probably the closest thing to you, I also did an AstroCamp back in 2019. And I remember that at first it was a little bit hard. I remember thinking, okay, so now for the next 2 weeks, I'll be studying uh, physics, and it's like, okay, one of the most difficult subjects on earth. I'll be speaking in a foreign language. And yeah, I remember the beginning was a little bit hard, but then at the end, I met a lot of cool people. Um, I studied astrophysics, and yeah, even though I quite enjoyed doing it for 2 weeks, I decided not to do it for the rest of my life. And then, I pursued a different path. I studied bioengineering in Porto. So I'll talk a little bit about the course. Of course, it's the course I did in Porto, but I think it's very similar to other faculties. Um, so, as any other engineering, it's the first 2 years is basically maths, physics, chemistry, programming, and in this case, in bioengineering, biology as well. And then the 3 years, we choose a branch, one of these three branches, biological engineering, which is more related to the food industry and the cosmetics industry. Then there's biomedical engineering, which was the one I studied, which is more related to applying technology to healthcare. For instance, bio devices, wearable devices. One of the fields that I ended up doing my master thesis, and now my research is using AI models in healthcare to predict diseases or different outcomes. But I will talk a little bit more about that. And then molecular bioengineering, which is more related to the pharma industry. So, talking a little bit about biomedical engineering, I'll talk about three subjects that I think it describes more or less what's biomedical engineering. The first is medical instrumentation. That basically I learned how to use electronics and electronic circuits to measure electric signals from our body. For instance, the EMG or ECG. In this video, you can see that I'm measuring uh, the activation of my deltoid and bicep muscles during this movement of lifting an object. And this can be used for instance, a rehabilitation program after a patient suffered a stroke or whatever. Then I also had a course on neuro engineering, which where I learned the anatomy and the function of the brain, as well as measuring the different signals that our brain produces. And here I'm using the blinking light that you saw. I'm using the blinking light to induce a specific signal in our brain that then we can record using that cap there. Um, we can detect that signal and that specific signal, and then we can control it to do a specific action that we want. For instance, this is very used, for instance, to control the wheelchair. And then medical image analysis, where we use AI to, as I said before, to predict diseases, to segment organs, and so on, to classify, for instance, a tumor, benign or malign, and that's basically it. Just drink a little bit. Right now, I'm working at Ineshktech, or which in their website they say it is a private non-profit association with public interest status focused on scientific research and technological development, technology transfer, advanced consultancy and training, as well as the pre-incubation of new technology-based companies. So it's a mouthful of keywords that basically means that Ineshktech tries to act as the bridge between academia and industry. So it's an institute where we try to use the new knowledge that is being created in academia research, academic research, and use it to solve real problems in the real world. It is a pretty big institute with 6 sites across Porto, Braga, and Vila Real, and it brings together 13 R&D centers that do their work across these 5 fields: agro-food, energy, health, where I'm inserted, industry, and sea. So inside Inestech, I am in the Center for Telecommunication and Multimedia, one of the 13 centers, and each center has different research groups. In my center, the CTM, I'm in the Visual Computing and Machine Intelligence Research Group. And inside this research group, I'm working on the Phase AI project, which is an European project that gathers several European research groups that work on innovating in AI models for medical images generation. From now on, I'll try to explain a little bit this title. So I'll break it up into 3 parts: medical images generation and artificial intelligence. I'll start with the thing that you probably never heard about, artificial intelligence. I'm pretty sure that you never saw any one of these icons. Of course, I'm kidding. Everyone uses AI now, but almost no one really knows how does it work. Especially the people that works with AI, me included, sometimes, or to be honest, most of the times, I don't really know what's happening. But in a very simplistic way, I'll try to explain the basics of AI and how these models work. So I'll start with a question and I'll ask, what's this in the screen? Yeah, it's a linear function. It's probably the simplest function in maths. And I remember when I was starting to study functions, I was told that, okay, a function is just a factory that gets a number and outputs another number, and changing the 2 parameters, the slope and the y-intercept for the same input, we get different outputs. And believe it or not, the simplest, the most basic function of maths is one of the building blocks of the most modern AI models. And of course, it's not only one or two or 100 or whatever, it's a million linear functions and how they are combined that form what we call the artificial neural networks. The artificial neural networks were inspired in how our brain works, how our neurons are connected to each other, and in the artificial neural networks, our little linear functions work as the neurons that are connected to another linear functions. Of course, there are other things that I omit to make it simpler, but let's say we start with some inputs, and then the first layer of linear functions outputs several outputs that go through another layer of linear functions through another layer, and then we get an output. And this is more or less the architecture of artificial neural networks. And so we have the model architecture, but we need to develop an AI model. We need a data set, so we need data specific for the problem we want to address. We then need a loss function that is basically a function that measures the difference between the model's prediction and the real answer, the ground truth. And then we need an optimizer. It's a mistake there. We need an optimizer because, well, since this combination of linear functions becomes really complex, we can't solve the best combination of slopes and y-intercepts to make the best model. We can solve that analytically. So we need an optimizer that through gradients find one a better solution. Most of the times isn't the best solution, but it tries to find one of the best solutions, one of the best combinations of slopes and y-intercepts, let's say like that, for our model. Okay, now let's see how do neural networks learn. So these artificial neural networks learn pretty much the same way as the biological neural networks learn through repetition. That's how we learn, and that's how these neural networks learn as well. So let's start with an example. I find it's kind of simple. So let's say we want to train a model to detect a dog in a picture. So we first gather a bunch of dogs pictures, and then, of course, these pictures are represented in pixels that contains the intensities for the three channels, the red, green, and blue channels that corresponds to the intensity for each color. And so we have numbers. We can give these numbers to our linear functions. And we initialize our model, our combination of slopes and y-intercept randomly. And we pass our image through that model. And let's say at first it predicts it is a car. Of course, it's not car as a let's say a numerical representation as well as dog. And then with our loss function, we measure this difference. And using an optimizer, we can update our slopes and our y-intercepts in order to in the direction to make the model better, to improve the prediction. And then we can continue to give a bunch of dogs pictures. And then at some point, our model predicts it is a cat. And at first you can say, oh, it's not quite there. But you can say that a cat prediction is much more close than a car prediction comparing to dog. But we can say now that maybe our model already knows how to detect an animal, how to detect animal features, but it can't quite distinguish between a cat and a dog. But it's on its way. So we keep using our optimizer to update the parameters. And at some point, after giving lots of dogs pictures, it says, okay, there's a dog in this picture, and we can consider the training is done. And hopefully when it sees a new dog picture, it will say there's a dog in that picture. So that's more or less how neural networks learn. Do you have any question? No, it's fine. So yeah, so I hope it's kind of clear. So let's move to uh, medical imaging. What is medical imaging? It's basically techniques that enable non-invasive visualization of the inside of the human body, and this way doctors can support diagnosis and monitoring of diseases. There are a bunch of techniques, but the most common ones are ultrasound, magnetic resonance imaging, aka MRI, X-ray, and computed tomography, aka CT scan. I'd like to ask if anyone knows what's in this MRI. The brain. Yeah, exactly. It is the brain. you can actually see the most peripheral zones are more white, which correspond to the white matter. And then the more central zones, they're more gray, which means they're the gray matter. And in this CT scan, does anyone knows? This might. Okay, lungs, more predictions. Yeah, it is the lungs. It's an axial slice of the lungs, of the thoracic region. We can see here these two more dark regions are the lungs. We can also see here it is the heart. We can see these two holes. It's the aorta artery. And the more intense zones, it's bone. We can see here the vertebra. And around the lungs, we can see some of the ribs. And here, these two lines are the scapula. So yeah, that's the most common types of techniques of medical imaging. And how can AI be useful in medical imaging? Basically, we use AI for three different tasks. Let's start with the simplest one, which is classification. So in this task, we give our model an image. So let's say a CT scan of the lungs. And what this model tries to do is the output is it says, okay, there's a lung nodule in this CT scan, or there's not a lung nodule in this CT scan. Then the more complex task is segmentation. So now this model not only says if there's a lung nodule, it also says where is it, which pixels in the original CT scan correspond to the lung nodule, and this way we can infer about the lung nodule characteristics such as size, shape, texture, and then we can use it to characterize as benign or malign, for instance. And then we have the more difficult task, which is generation. So our model tries to learn based on real images. It tries to learn the features and the patterns of our data set, and then it generates new images, synthetic images, hopefully with the same characteristics, not exactly the same. So it's not a reconstruction, but it keeps the features. So let's say if we give a CT scan with lungs, heart, nodule, a body, envelope, and so on, then our model also needs, or hopefully it outputs a CT scan with the same color intensity ranges, with the same anatomies, and so on. I'll just drink a little bit of water. So I hope now AI and medical images are more clear. I'll talk very briefly about generation, about image generation with AI models. And basically, right now, the most common models used to generate images are the so-called diffusion models. That basically works as we start with our real images, with our original images, and step by step, by little steps, we start adding Gaussian noise, random noise, and we start deteriorating our image until after these steps, we have random Gaussian noise image. So it has no information, it's just noise. And while we do these small steps, we have our model learning how does this process works, and it also learns how to do the reverse path. So it learns how to denoise an image. So after training a diffusion model, then we can give just a volume of a random Gaussian noise, as it's here, and then the model knows how to reconstruct an image and get the similar features as the original data set. That's more or less how diffusion models work, and why are these models, why we can increase the amount. So we need a lot of data to train these models. These are deep learning models that need a lot of um, information to learn. And then, especially in healthcare, we don't have access to a lot of medical images because, well, they're private and it's difficult, it's very difficult to share between cohorts, between labs, information. So we have a problem of scarcity of data. And being able to generate synthetic medical images, it copes with those problems. It increases the data set, and it's easier to share this data since it contains no personal information. And then the end goal of generating synthetic medical images is to improve the performance of automated diagnostic models. So if we increase the amount of available data, and you can also we can also control the diversity of pathological scenarios because since we are generating images, we can say, okay, I want a lung nodule with this specific shape because my real data set doesn't have a lot of those. So I want more of this specific shape or of this specific size, and we can shape our data set and using more data. And of course, if this synthetic data is similar to the real data, if it follows the same distribution, if the model creates good synthetical medical images, it will improve then the performance of the other models, such as classification and segmentation models, which then uh, are very useful to, as I said, to predict diseases and uh, um, segment organs and nodules, and then classify it, for instance, the tumors as benign or malign. And I think that's it. I hope I made this topic a little bit clear for you guys. Thank you for your attention, and now I'm open to questions.